Hello everyone, today we're going to talk about Wiener filtering. The prerequisites for this material are linear regression, discrete Fourier transform, linear translation invariant models and convolution, and stationary signals and PCA. We're going to consider the problem of signal estimation where we want to estimate an n-dimensional signal y from n-dimensional measurements x. We model both x and y as random vectors. You can think of x maybe as a noisy version of the signal y, and we want to remove the noise to estimate the signal. Like this is the image denoising problem or signal denoising problem that we have considered previously. The optimal estimate in terms of mean squared error, if we know the joint distribution of y and x, is just the conditional mean of y given x. We already talked about this when we introduced linear regression. The problem is that we don't know the joint distribution. We have to estimate this from data, and when n is large, when the number of features, which in this case is the dimensionality of the measurements, is large, it's usually not tractable to estimate this conditional mean. Again, as we had discussed when we were talking about linear regression. So for this reason, we're going to consider a linear estimate. Okay, so I want to draw a picture to make it clear. So we have y and we have x. If I manage to draw a rectangle, okay, let's imagine that the two rectangles have the same size. And the idea here is that we're going to map x to y using a linear transformation, and therefore just applying a matrix, a square matrix. Let me try again. But we're going to just pretend that this is a square matrix. Let's pretend this is a square matrix to y. Okay? We call this matrix B transpose. If we care about mean squared error, which is the expected value of the L2 norm of the difference between y and the linear estimate, then that just decouples into the sum, by linearity of expectation, into the sum of the expected value of the error that we make, the squared error that we make for each entry. And the linear estimate for each entry, interestingly, only depends on the corresponding row of the matrix. Why? Because if you want to estimate the first entry of y, that's going to be the first row of B transpose times x. Want to estimate the second entry of y, is going to be the second row of B transpose times x, and so on and so forth. So this decouples into n completely separate linear regression problems. Each of those linear regression problems, we know what its solution is going to be. And if you don't remember, you go back to the lecture, the video on mean squared error estimation. But basically, we have a feature which is the jth entry of y, and we have a response with not a feature, a response that is the jth entry of y, and we have features which are the entries of x. Okay, and the best linear coefficients, by the way, here we're going to assume that y and x are zero mean because we can center everything, as we already explained when we were talking about linear regression. Okay. The best linear estimate is just given by the inverse of the covariance matrix of the features times the cross covariance between the features and the response. So that's the solution to the jth linear regression problem. We have n of them. Okay. Here I've realized that I should write big N here. Sorry about that. Okay, so if we put all of this covariance between the features and the entries of y in a matrix, that matrix is called the cross covariance matrix. So here the first row has the covariance between the entries of x and the first entry of y. The first column. The second column has the covariance between the entries of x and the second entry of y, and so on and so forth. This allows us to write the matrix B as just the inverse of the covariance matrix of x times the cross covariance of x and y. Okay, because each of these guys here is one column of that matrix. Okay, so one column is given by this product. If we when we do this product, we're basically applying this matrix to each of these columns. So this is equivalent. Okay, this gives you the jth column of the best linear estimator. This gives you the whole matrix. Okay, so now we have a solution. This is the best matrix that we can apply to x to map it to y and minimize mean squared error. So are we done here? Well, as we discussed when we were motivating linear translation invariant models, we are not done, because if we naively estimate this covariance and this cross covariance from data, we're going to have a tough time, because they have n times n parameters, okay, n squared, and for a lot of the signals that we're going to be interested in, such as images, audio, and so on, n is at least 10 to the 4 and often a million or more. So these matrices are going to be 1 million times 1 million. So basically forget about it. You're not going to be able to estimate them from data. However, these signals often have translation invariant statistics. And as we will see, and as we already mentioned when we were motivating translation invariant models, this is going to be super useful. Okay, so we already introduced a definition for stationary signals, and we showed that their PCA had this very special structure that we'll review in a moment. These signals are modeled as having a constant mean. In this case, we're just assuming everything has zero mean. So here you could just think that mu is 0, because we can always center the data essentially. And their covariance structure, so the covariance between the entries of the random vector x, only depends on the difference between the indices. Okay, so basically this means that if you have this vector, the covariance between the first and the fourth entries is exactly the same as between the 11th and the 14th entries. Okay, that covariance is given by an autocovariance function that only depends on the difference. Remember that we're doing everything mod n, but you shouldn't worry too much about it. This just produces some edge effects that you have to deal with when you deal with real data. But the point is that the covariance only depends on the difference between the indices. As a result, you get a covariance matrix where each column is a shift of the other columns. And because applying this covariance matrix is essentially like applying, like doing a convolution with that row, we have that the eigendecomposition has eigenvectors that are discrete sinusoids. They're basically these basis functions from the DFT matrix. And the eigenvalues correspond to the DFT coefficients of this autocovariance function. Okay, so that's going to be very important. It's also really important to realize that now, if we want to learn this covariance matrix from data, we only need to estimate the autocovariance, which has n parameters as opposed to n squared. So this is going to be tractable to compute from data. Okay, so we have kind of solved our issues with the covariance matrix of the data, okay, with this covariance matrix of x. But what about the cross covariance between x and y? That's still problematic. Well, it turns out that often signals have cross covariances that are translation invariant. We call these signals jointly wide sense or weak sense stationary if each of them separately have stationary statistics, so constant mean and translation invariant covariance, and if their cross covariance is also translation invariant, meaning that if we take a look at x and y, the covariance between the first entry of x and the first entry of y is exactly the same as the covariance between the second entry of x and the second entry of y, and the third entry of x and the third entry of y, and so on and so forth. Okay, it's exactly the same. Similarly, the covariance between the first entry of x and the second entry of y is exactly the same as the covariance between the second entry of x and the third entry of y, and so on and so forth. Okay, it only depends on the difference between the indices. Again, we have this mod n, but don't worry too much about it. Okay, so this basically means that the cross covariance is also shift invariant. And again, this means that now we only need to learn n numbers. Okay, we only need to learn this cross covariance function that only depends on the difference between the indices to characterize the cross covariance between the two random vectors. So this is going to become tractable. In addition, the cross covariance matrix is going to have this special structure because of this translation invariance, where each column is a shift of each other column. Okay, the columns are basically this cross covariance function evaluated at 0, 1, 2, and so on. So as I mentioned briefly previously, when we have a matrix that has this structure, a circulant matrix, where each column is a shift of every other column, its eigendecomposition, as we proved, consists of eigenvectors that are DFT basis functions, so discrete sinusoids, and eigenvalues that are the DFT coefficients of the columns of the circulant matrix. So this means that for the cross covariance matrix, the eigendecomposition gives this sinusoidal eigenvectors, and the eigenvalues are just the DFT coefficients of the cross covariance. So now we can go back to our formula for the best matrix that maps x to y, and it turns out that that matrix that maps x to y is going to be given by this expression. When we compute the inverse of this, remember that if you have the inverse of A, B, C, this is just equal to C inverse, B inverse, A inverse. The inverse of this guy is the inverse DFT matrix, which is just exactly this. The inverse of this guy, this is a diagonal matrix, so you're just going to do 1 over the entries of the diagonal. And this is the inverse DFT matrix, so its inverse is just a DFT matrix. Okay, so basically we end up with the inverse of this being this. And now we have an interesting cancellation here, where we have a DFT matrix and its inverse, so that we realize that this matrix B has a very special structure. It has an eigendecomposition that corresponds to DFT matrices, and these are diagonal matrix in between, where we're just taking the DFT coefficients of the cross covariance and dividing by the corresponding DFT coefficient of the autocovariance. This means that this whole matrix is actually circulant. So it's exactly equivalent to applying a convolution, which is pretty cool. We have assumed translation invariant statistics, and we end up with a convolutional model, which we already introduced like 2 videos ago, with the motivation of performing a more efficient linear estimation. So this actually just follows from this assumption that the signals have stationary statistics. Under that assumption, this is actually the right thing to do, to just apply a convolution as opposed to a generic matrix. Okay, so equivalently, we're applying a convolution, but equivalently, the optimal linear estimate weights each Fourier coefficient separately. Okay, and now we're going to justify this by seeing how the weights that we have computed, which depend on the DFT coefficients of the autocovariance and the cross covariance, how they depend on the Fourier coefficients of the measurements and the sector. So it turns out that if we look at the covariance matrix of the Fourier coefficient of x, so just to be clear, we have defined the Fourier coefficients of x like this, because I couldn't just put, like, I didn't want to, I mean, with our notation, we would have put a triangle on top of x, but that looks it looks like too much, right? It looks very ugly. So that's why I'm using this other notation for the DFT coefficients of x. And now we want to see what the covariance matrix of the DFT coefficients of x are. So by definition, it's equal to that. And now we are going to apply linearity of expectation to take the DFT matrices out, and we end up with the covariance matrix in here. Okay, this is just the covariance matrix. This is just the covariance matrix of X by definition. And now we know that this guy has this eigendecomposition under the assumption, of course, that X is White-Sense stationary, where we have the inverse DFT matrix and the DFT matrix. These guys cancel out, and we end up with showing that under stationary assumptions, the covariance matrix of the DFT coefficients of X is actually diagonal, which means that the DFT coefficients are uncorrelated. That's not immediately obvious. Under stationary assumptions, if you do COF of the kth and the lth DFT coefficients of a signal that is White-Sense stationary, this is going to be 0. That's an ugly looking 0. This is all going to be 0 because this guy is diagonal. Okay, so the off diagonals are 0. Again, that's not immediately obvious. Something else that is really interesting here is that the variance, which is the diagonal of the covariance matrix of each of the DFT coefficients of the matrix, is just given by the corresponding DFT coefficients of the autocovariance functioning. Okay, this is not obvious. Now we're also going to analyze the cross covariance between X and the DFT coefficients of X and Y. Okay, just by definition, it says we take the expected value of fx times fy adjoint. The f's come out. This guy is just the cross covariance matrix. We know that the cross covariance matrix under this joint White-Sense stationary assumption has that eigendecomposition, so there's going to be that cancellation there. And now, and this is pretty cool again, under this joint stationary condition, what we find is that the covariance between xf k and yf k, sorry, not k, L, this is the whole point, L is 0 if k is different to L. So the DFT coefficients corresponding to different indices of X and Y are actually uncorrelated. This tells you immediately that you can forget about the interactions between the different Fourier coefficients and just estimate each Fourier coefficient of Y using just a single Fourier coefficient of X, namely the one that has the same index. And it turns out that the covariance between the Fourier coefficients of X and Y is just given by the DFT of the cross covariance, which again is not immediately obvious. So this is kind of cool because now we go back to our estimator, this convolutional matrix that has this eigendecomposition, and the entries in the diagonal are super intuitive. You just take the covariance between the corresponding DFT coefficients of the signal and the measurements, and you divide by the variance of the measurement. This is essentially like taking each DFT coefficient of the signal and estimating it separately. So this translation invariant linear estimator that we have derived is actually called the Wiener filter, which is a really fancy name in honor of Wiener, which came up with this kind of stuff. But, beyond that fancy name, it's essentially just a linear estimator where we're assuming translation invariant statistics. That's all it is. So if X and Y are 0 mean, again, this is not a big deal because we can just center, and this is a much bigger deal, jointly stationary, the linear estimate of Y given X that minimizes the mean squared error is a convolution, as we have shown, with a filter where each DFT coefficient is weighted by the covariance of the data, the measurements and the signal divided by the variance of the measurements. Okay? And here X and, as I already said, XF and YF denote the DFT coefficients of X and Y. Okay? Okay, so that is the Wiener filter. Now, in order to gain some intuition about why, it makes sense, and what are its limitations, we're going to derive it for the problem of denoising. So we're going to have measurements that are equal to a clean signal Y plus some Gaussian noise with a certain variance. Because we're going to assume stationarity and apply Wiener filtering, we're going to be interested in the DFT coefficients of the measurements, which are going to depend on the DFT coefficients of the noise. So an interesting question is, this Gaussian noise, how does it look in the Fourier domain? How do the DFT coefficients of that Gaussian noise look? And it turns out that linear transformations of Gaussian vectors, as we have seen before, are just Gaussian vectors with a mean that is a linear transformation of the original mean. In this case, the mean is 0, so we don't have to worry about this. And a covariance matrix, which is the same covariance matrix, but with this linear transformation applied on the left and on the right. When that linear transformation is the DFT matrix, we have this factor of n, because remember that the inverse of the DFT matrix is 1 over n times the adjoint. But essentially, the Gaussian coefficients remain IID, because this is going to be a diagonal matrix. Okay, here we're using the fact that f times its adjoint is just n, where f is n times n, times the identity. Why? Because 1 over n f adjoint f is just equal to the identity, because that's the inverse DFT. Okay. So the point is that the noise is going to be IID Gaussian with variance n sigma squared. So now to derive the Wiener filter, we need to compute the covariance between the DFT coefficients of the measurements and the DFT coefficients of the signal, and the variance of the DFT coefficients of the measurement. Okay, so what's the covariance of the DFT coefficients of the measurements and the signal? We remember that the measurements is the signal plus the noise, so this decouples by linearity of expectation. And now these guys, I haven't actually said it, but it is written back here, and it's pretty crucial. We're going to assume that, sorry, I hope you're not getting dizzy with all of this. We're going to assume that the noise is independent of the underlying clean signal. And under that assumption, their covariance is obviously 0. So let's go back here. And sorry for going back and forth. The covariance between the noise and the signal is 0. Okay, so we end up with the covariance between the signal and itself. So that's just the variance of the signal, in particular of the kth DFT coefficient of the signal. And when we consider the variance of the measurements, again, the measurements are just equal to YF plus CF, but these guys are independent. So their variance is just the sum of their individual variances. The variance of the sum is equal to the sum of the variances because of independence. And now this is just the variance of the noise, which is we know is n sigma squared, and this is again the variance of the signal. So when we plug this into the expression we derived for the weights that are applied when we apply Wiener filtering, we get this expression which we should kind of sanity check to see if it makes sense. And a good sanity check in this kind of problems is always to see what happens if you have no noise or if the noise is very large. So if we have no noise, this is 0. So this whole thing is equal to what? Think about it on your own. It's going to be equal to 1, which means if there's no noise, leave the signal alone. You're just going to apply this weight to the DFT coefficients. You're going to leave it alone. Now what happens if the noise is super, super large? If the noise is super large, then this is going to be very, very large, much larger than this and than this. So this whole thing is going to go to 0. So you're killing the estimate. You're saying, let's just estimate 0 because the noise is so large that I cannot see the signal. So that makes a lot of sense. In between, you're kind of doing a trade-off between the variance of the signal and the variance of the noise. So you're taking your measurements, each individual DFT coefficient separately, and you are making it smaller if you think that the variance of the noise is going to be large with respect to the variance of that particular DFT coefficient, and you're kind of leaving it alone if you think that the variance is going to be small. The variance of the noise is going to be small with respect to the variance of that DFT coefficient, which makes a lot of sense. So now let's see what happens if we apply this to audio data. We need to compute the variance of the Fourier coefficients of the audio data. When we do that, this is what we get for the data set that had like someone saying yes, no, and so on. Okay, we see that there's a lot of energy in the low frequencies, not so much energy in the higher frequencies. This is very typical of real signals. So now what we do is we apply this weighting. The noise is the same in all frequencies, okay, because it's IID Gaussian noise. What's going to happen is that when we apply, when we apply this formula that we had for the Wiener filter, in places where the variance is high, where the Wiener filter is basically going to leave the signal alone, in places where the variance of the signal is low, we're going to suppress those DFT coefficients. So because the signal is high, the signal energy is high in the low frequencies, we're going to preserve the low frequencies and kind of kill the high frequencies. Again, depending on how much noise there is. So when there's not a lot of noise, this is what the filter looks like in the Fourier domain. We're suppressing high frequencies, but not that much. This is what the convolution, the equivalent convolution of applying this Wiener filter looks like. So we're convolving with this, and we're multiplying with this in frequency. Okay, that's the Wiener filter that is performing denoising. Okay, so this one there's not that much noise. This one there's more noise, so we start to kill the high frequencies more because we believe that their variance is small with respect to the noise. As you can see, in time we're convolving with something that smooths out the signal more. And where there's even more noise, we start really killing the high frequencies. Remember that we're multiplying with this, and this is a logarithmic scale, so we're really killing the high frequencies. And we're convolving with something that is, that smooths out. Equivalently, we're convolving with something that smooths out the signal. Okay, so this is the clean signal. This is the noisy signal in the time domain and in the Fourier domain. And this is the denoised signal. So you can see that the noise is, being removed to some extent by killing the high frequencies so that they look more like the clean high frequencies. Okay. So this is an example with sigma equal to 0.1, so not that much noise. This is with more noise. Okay. And realize that we are killing the high frequencies here. This is the DFT coefficient of the denoised signal, more than we should probably. But that's the problem with Wiener filtering. You have a lot of noise in the signal. You're applying this convolutional filter. It has to smooth out the signal to kill the noise, but it also kills the signal along with the noise. Okay, so here you can actually see that the denoised signal is a smoothed out version of the noisy signal, but it doesn't approximate the true signal as well as we would like it to. Okay, this is an example with image data, very noisy signal. These are the variance of the DFT coefficients of image data computed over a database of images. Realize that this is logarithmic. We have that the low DFT coefficients have the most energy by far. And when we compute the Wiener filter for certain noise levels, again, what happens in frequency is that we're going to leave the low frequencies alone and suppress the high frequencies. Here, not so much because the noise is low. This is the same as convolving with this filter. By the way, you might notice that this. That's because the images that we have in our database have a lot of edges, or is horizontal and vertical edges. So that's why there's more energy in frequencies that are exactly aligned like that. So basically that says that these basis functions that look like this, as opposed to the ones that looked like that, if you remember the multidimensional DFT basis functions, it's telling us that these guys and these guys contain more energy in the images than the ones that are tilted. Okay, that's why we see more variance. If we go here, that's why we see more variance in this direction. Anyways, so applying the Wiener, the expression for the DFT filter, the Wiener filter that we have derived, when we apply it, what happens is we're killing again high frequencies. Not so much when there's not that much noise, but when there's more noise, we kill them more and more, which is equivalent to convolving with this filter here that essentially smooths out the signal. Okay, this is especially apparent here. We're smoothing out the signal essentially over 8, like an 8 by 8 square of pixels. I mean, of course, it's not a square, okay? Like the filter looks like that. But all I'm saying is that you can think of this as a local averaging of the pixels that smooths out the image. Okay, you can see this here. You have the clean image, the noisy image, and the denoised image, and the corresponding DFTs. Okay. It's interesting how you can see that because of these lines that we have here, you can actually see them in the 2D DFT. When we have higher noise, again, we kill the noise by killing the high frequencies, but the problem is that we over smooth the image. So this is the main problem with Wiener filtering. And this is actually not surprising, because realize that we're applying exactly the same filter all over the image. We're convolving this all over the image. And that's a very strong limitation of Wiener filtering. Okay, we're smoothing out the image by killing the high frequencies, because we observe that the variance of the high frequencies, the energy of the high frequencies in the signals is lower than in the low frequencies. But the problem is that we are applying the same filter all over the image. It would make a lot more sense to try to adapt to features such as edges and so on, which we have seen can be achieved by nonlinear estimators such as thresholding with wavelets. Okay. So what have we learned here? Under stationarity assumptions, the optimal linear estimator is basically just reweights the Fourier coefficients of the signal based on the joint statistics between the signal and the measurements. And under stationarity, those joint statistics can be estimated from the data because they just depend on the autocovariance and the cross covariance, or equivalently on the covariance and variance of the Fourier coefficients of the signal and the measurements. When we compute this out, essentially we get an estimator that is equivalent to convolving with a fixed Wiener filter. We call it a Wiener filter. It's just a filter that comes from, that is derived by this Fourier coefficient weighting. The issue with that filter is that it does not adapt to individual signals. So in the examples we saw for sound and for image, it kills the high frequencies and it is not able to adapt to important features such as edges. We're going to see that more sophisticated algorithms based also on translation invariant assumption, which are convolutional neural networks, are much more effective in adapting to the signals, and in actually they're the state of the art for this kind of problems, for image denoising and so on. But that's for the next video. Thank you very much.